Subscribe to this YouTube channel by clicking the subscription button below. For future webinars and online short courses, please visit our website at australianwaterschool.com.au. Welcome to this Australian Water School webinar brought to you by IceWarm. This highly regarded webinar series engages leading thinkers in the water sector globally, and today, no exception. Robert Chahorski, Chris Goodell, and Craig Price will lead the discussion on roughing it for water modelers. Hi, my name's Trevor Filler. I'm the National Partnerships Manager here at IceWarm and Chair of the Australian Water School webinars. And it's a great pleasure to welcome you from all over the world. Well, millions, yes. Well, not quite millions, but quite a lot of people. There you are, all are. Oh, look at that, especially in North America. Oh, that's great. That's fantastic. But this is what's coming up. Free webinars the next week and the week after. We do this every month. And then I just want to really highlight that one in yellow, modelling structures in HECRAS. You won't want to miss this if you are doing bridges, culverts, etc. around water modelling. 5th and the 12th of March. Go on the website, register. Very low cost, and it's really, really top-end professional training. Today, we're going to get straight into it. Robert, Chris, and Craig, thanks so much for joining us, gentlemen, from all over the world. Robert's Principal OHM Advisor and President of H2O Metrics, cloud-based smart water and sewer data application platform. Chris Goodell with Kleinschmidt Associates, Principal Consultant for Hydraulics and Hydrology there. Chris is the developer and primary author of RAS Solution, a big HECRAS blog, really interesting blog, author of the book, Breaking the HECRAS Code. And Craig Price, Surface Water Solutions, civil engineer and project manager with international experience in water resources, and especially with the US Army Corps of Engineers, and a fantastic trainer. All three are, but we're working with Craig for a long time. Chris, Craig, Robert, thank you for joining us. Where are you all from? Chris, why are you doing this, Chris? Give us one sentence each, Chris, Craig, and Robert, and where you're from, and what on earth time it is for you. For me, it's a great little 9:30 a.m. in Adelaide, South Australia. What about you,
Chris? Here in Portland, Oregon, on the northwest side of the U.S., it's 3 p.m., just a little bit after. So,
didn't
not
look
a
like
bad
3
time
a.m.
to do a webinar.
Wonderful, and you're keen for this area of work to come to the fore.
Oh yeah, I use N values every day. Every time I run a HECRAS model, N values are a big part of it, and there's always a big question around it too. It's a big part of calibrating your model and really upping the game and improving the quality of your models is choosing the correct N value and then making sure you calibrate it correctly.
Just looking at the number of people here today, that they also agree with you on that. Craig, yourself?
Yeah. Oh, yes, same. It's just such a subjective factor. I just thought Chris and I and Robert were talking a while back about what might make a great topic. And it's just one of the questions that comes up in training courses all the time. You get these preset pictures that say, hey, if this is what your channel looks like, this is what your roughness should be. But it's a little more involved than that. And we've got billions of dollars of infrastructure being built around somebody's, just random pulled out of the air number. No, we should be giving it a little more focus and giving a little more attention and running our sensitivities on.
Now, this guy Mannings was an accountant. Anyway, I'm going ahead of the game. I'm going ahead of the game.
We'll hear about that. Yes.
No worries. And Craig, you're in Australia, in the
the west side of Australia, so bright and early in the morning here, but excited to be on board with my old former classmate Robert on the other side of the world. We're about as far apart as we could possibly be. If I drove a line right through the planet, I'd probably hit you on the other side there.
Might poke out where Robert is right now. Where are you, Robert?
I'm in the Midwest part of the United States, in Michigan. It's 6 p.m. here in the evening. We like to represent the state of Michigan around here as a hand. So for those around the world, this is Michigan, and I'm in the Detroit area, which is right about there.
I get that. I get that now.
I love geography lesson. The reason I'm doing this is I'm a hydraulics modeling geek. Really enjoy working with modeling and equations. And I think there's no better way to get to know an equation than to try to program it into a computer and represent it inside of software. I've done that. I know Chris has done that. And I think that's what I'm excited to talk about today.
Fantastic. Well, you can all see this is a fantastic team, and we are so delighted to have them. We're going to get underway right now. Craig's going to do a short intro and a really interesting intro. I've seen this, and you won't want to miss it. Okay, over to you, Craig. We'll leave it with you.
Okay, excellent. Great to be on board with Robert and Chris. We'll hear mostly from them. I'm just going to do a brief intro to set the stage, and we'll hear about kind of two different applications of roughness coefficients. Robert focuses, I think, more on pipes and the roughness elements that can come into your pipes in all sorts of forms, sometimes unpredictable forms. How does that affect your flow, and how does it affect your velocities, and how does it affect your flow depths, your shear stresses? By picking this number that's supposed to represent how rough it is, what does that do to your hydraulics? So Robert will talk a bit about the history of Manning's equation and some of the alternatives, and then also get in more on the pipe side of things. Chris is going to focus more on the open channel flow. These are some old photos, and you'll find, I think, dozens of old USGS manuals with pictures of streams and what the roughness should be. Now, obviously, that's, how that affects your flow is going to depend on how deep your flow is. Down here at the boundary, at the interface, it's always going to be zero. You're not going to have any flow right in the boundary layer, but that could be a very small boundary layer, or it can be a very large one. And as you're looking at the flow in the center of the path, your roughness around the outside is going to affect your flow in different ways, depending on how deep you are with your water depths relative to the roughness elements. And just to put things into scale here, if you're a fan of old 80s movies, I think this was one of them, where, if you imagine his yard getting flooded by, a deluge a meter or two deep, what would these grass blades represent roughness-wise to that flow? And might you get by with a Manning's roughness of, say, 0.03 or something like that? That might be reasonable here. But when the sprinklers come on, and you see here in Hollywood Studios, they've rebuilt this world here. Well, when you have sheet flow, those roughness elements end up stretching out to a very large scale, and maybe you would actually be using a roughness coefficient of, say, 0.1 or higher to represent flow that's being obstructed by this forest of grass blades. With that, what I wanted to do is just ask one brief question to everybody on the call here relative to a hydraulic model. Now, this is one of the dummy models that we've set up in our classes with iSwarm, using the same examples that we set up from scratch there. When we're looking at some flow here, and let's just turn on our water surface elevation across a cross section here. And if I were to represent the channel with a roughness coefficient of 0.03, which I've got here, I've got a given flow depth and a given flow velocity. Now, what if instead of 0.03, which is pretty smooth for a natural channel, what if I went up to 0.06 or to 0.1 or something higher than that? I should use this as a poll question, but I won't do that right now. As we look at this, this water surface elevation right here, if I were to roughen up the channel, roughen up the entire domain that I'm modeling here, would this water surface elevation go up or would it go down? Is this intuitive? And so in most models, I think everybody would answer the question up, right? If I were to roughen this up, it would represent more friction, more frictional resistance, and it would push the water surface up. Well, if I turn on my 0.06 and my 0.1 roughness values here, and I plot the same thing, I actually get the opposite effect. I get a roughness or a water surface elevation that's coming down. Here's my 0.03, here's my 0.06, and here's my 0.1. Well, how did a rougher ground surface lower my water surface elevation? And this is something that we walk through in some of our courses. Sometimes when you roughen it up, it actually sends flow the other way upstream, and you're looking at less flow. In this particular case, what I'm looking at here is a rain on grid model, a direct precip model. We've had some webinars on that in the past that you might want to have a look at. And what actually happens is as you roughen this thing up, you're slowing down the response of the watershed, of the catchment. You're attenuating your peak flows. So my smoothest roughness coefficient actually ends up with the highest peak flow because the water barely even gets there when I roughen it way up. It gets there a lot slower and less of it gets there, and it attenuates the peak flow. So I'm actually looking at 3 different hydrological situations, not just 3 different hydraulic situations. So it's not always as cut and dry, as straight intuitive as we might think. It doesn't always correspond linearly that, the rougher your channel is, the deeper it will be. There are other elements to consider, and I'm looking forward to hearing from the other speakers today. I'll leave it at that, turn it straight over to Robert.
All right, thanks, Craig. That's just a great example of how sometimes things in hydraulic modeling can be counterintuitive. Always good to keep that in mind. So today in my part of the talk, I'm going to cover these 3 items, talk a little bit about various roughness methods, and then dive a little bit into some details of the Manning's equation and get into some overview and history. And then I'm going to wrap up with a few specific applications to pipes. So let's just dive right in and get into a couple different methods for computing roughness. First one I think we have to start with is the Moody diagram. This is probably the most generic and comprehensive way to represent roughness in conduits. What the Moody diagram does here is it relates a friction factor here on the y-axis to the Reynolds number going across on the x-axis. These various curves, each one essentially represents a different type of pipe material, different roughness level of pipe materials. And then it's really probably the most accurate representation of roughness because it accounts for the roughness over various flow regimes with the Reynolds number, and also in laminar flow and in turbulent flow, all in one kind of magical diagram. Interestingly, it's not used that often in practice because it's just hard to represent this complex graph in a spreadsheet. So that's kind of interesting. But you'll notice that all these curves, they all flatten out as we go to the right side of the graph, which means as we get into really high Reynolds numbers, really turbulent flow, which is mostly what we usually have in nature and in conduits anyway, all these curves flatten out, which gives us a real nice opportunity to simplify this process. And we're going to talk about that next with a couple of the other roughness equations. But it's also worth noting as we move to the left side of the graph, notice that these curves, they curve up quite a bit to the left. And so I think that's just important to keep in mind that when we do some of these simplifications, it might not be a bad idea to check what your Reynolds number is, especially if you're doing a model or an application where there's some really critical thing you're designing, like perhaps a flood level that might impact millions of people or lots of property. Probably not a bad idea to check your Reynolds number and look at the Moody diagram and just make sure you're not operating over here in this part of the graph where all the curves get steep and the friction factors go up a lot more than you might expect from some of these other equations. So just a note of caution there. Okay. Next method I want to talk about a little bit is the Hazen-Williams equation. This is one that is commonly used in practice. It's an empirical equation, a simplification of the Moody diagram and of roughness. It was developed really to describe the flow of water in pipes, drinking water systems. It makes use of a C factor for its roughness equation. And I think because it was developed for flow of water in full pipes, it is most commonly used in water distribution systems. But it is one of those roughness equations that you will see out there in practice quite a bit because it is very easy to represent in a spreadsheet. And then moving right along to kind of the star equation of our webinar today, the Manning's equation. Again, it is also an empirical equation. It describes flow and head loss and friction in conduits and channels. It makes use of a Manning's N for establishing roughness. And the opening poll question was a little bit of a joke. None of the presenters today actually knew what the Manning's N stood for, so we thought we'd put it on the webinar attendees and see if anyone had a good idea of what it was. Looks like a lot of people chose nothing, which is kind of where we were all at with it. So. But Manning's equation is commonly used in hydraulic modeling in conduits and pipes. It's very easy to represent in a spreadsheet or in a computer program, so it does have widespread use for that purpose. So with that, let's get into the details of the Manning's equation a little bit and get into Manning's himself a little bit. So I want to start with true or false, and Trevor dropped a little hint to this already in the beginning, but true or false, Manning's background was in accounting. And I'll give you just a second to kind of form your answer in your head, probably figuring out I wouldn't be asking this question if I wasn't going to try to surprise you and tell you that this is true. Manning's was not an engineer, he was an accountant. I think this might have been one of his strengths because it let him define the simplest solution to match the data. He looked at data from many different watersheds, and he had several equations, I think a half a dozen equations that were there that he was looking at that described this dynamic. And he was looking for what is the simplest equation that kind of represents them all. And that led him to find the simplest solution that's also sometimes known as Occam's razor. So kind of interesting little tidbit about Manning's. Manning was born in 1860 in Normandy, France. So we're talking about, a couple 100-year-old equations in process here. So no, I don't think the N in Manning stands for Normandy, but who knows, maybe it does. He proposed the Manning equation in 1889 at the age of 73. So he was a late bloomer. I think that gives us all hope that we all have an opportunity to bloom later in our careers. So there's always good things ahead, right? So Manning's can give us all hope. There were two things that Manning did not like about his equation. One was the need to use a cube root, and you'll see that in a second when I put the equation on the screen. Back in the day when Manning's put his equation out in 1889, computing cube roots was hard. There were probably tables for looking up square roots, and squaring something is easy and just multiplying it by itself. But that cube root is a tricky thing, and Manning's did not like that. Manning did not like that. And then the next thing he didn't like is the fact that the equation is technically dimensionally incorrect. And I think that's one of the great ironies of the Manning's equation, is one of the most widespread equations in civil engineering, and it's not dimensionally correct. So take that for what it's worth. And then finally, Manning's equation was made famous in King's Handbook of Hydraulics, which was first published in 1918. Note that that's almost 30 years after Manning proposed his equation. So I think that just shows sometimes how slowly things can move in our practice in civil engineering. So just some interesting little bits of trivia there about Manning. Next, let's get to the Manning equation itself. So this is a pretty common form of the equation. On the left-hand side, we've got flow, represented as Q. On the right-hand side, first we have the Manning's N. That represents the channel roughness. Notice that the N is in the denominator of the equation. Typically, always higher N values are rougher channels. So in this case, all things being equal, a higher N would decrease the flow. Now, as Cray showed us, all things aren't always equal, and modeling can get complicated, and systems are complicated. But in this case, all things being equal, a higher N in this equation, in this form, would reduce the flow. Next in the equation, we have A and R. That's the area and hydraulic radius of the conduit. This brings in the channel geometry. Note the R, the hydraulic radius, is raised to the 2/3. There's that cube root. So you can get R squared easily, but then you got to take the cube root of that to get R to the 2/3, and that's what bugged Manning. And then finally, we have slope there, raised to the half power. That is the slope of the energy grade line in the most general form of the equation. Very often, you'll see engineers set that slope equal to the slope of the channel conduit. That's often done in modeling or to compute things like uniform flow. So it's a quick introduction to the form of the equation. I'm actually not going to go into a lot of more detail into the equation itself, but I'll take this opportunity just to kind of plug my blog. I have a very detailed article on my blog about the Manning's equation that goes into a lot more detail, and many other articles that I maintain on the water blog at h2ometrics.com/blog. So if you're interested in some water topics or more details on the Manning's equation, feel free to take a look at that there. Getting a little bit into the details of Manning's N for pipes. The poll question related to this: what's a typical Manning N for concrete pipes? Just making a note that it can vary there from a value of, at the smoothest, 0.010, and on the rougher side, 0.016. Notice the pipes in the photo are very smooth. The Manning's N just depends on how the pipe is finished, and you can have different characteristics of how pipes are cast and how smooth they get. So I think the pipes in the photo here are very smooth. Those would probably be on the lower side. And then rougher pipes, obviously, on the higher side. But also, in addition to the smoothness or the finishing of the pipe, I think it's important to keep in mind that Manning's equation is an empirical representation of a very complicated complex dynamic. And part of the variation on Manning's N is just to deal with some of the uncertainties. And that's kind of a note of caution I want to offer up next. Take the range on the Manning's N as a note of caution. The equation itself is not perfect. It's empirical. It's designed to simplify a very complex phenomenon. So just keep that in mind when you're evaluating the impacts on your engineering decisions, and maybe do some sensitivity and just be aware of the inherent variabilities in, first of all, picking the Manning's value, and next, just the inherent empirical nature and variability in the equation itself. So I just wanted to give you that note of caution. Next, I'm just going to talk quickly about a few applications to the Manning's equation for pipes. I'm going to do this all at once on one slide with 3 examples. First, on the left-hand side, we've got the same equation I had on the screen a moment ago. In this case, we could set the slope equal to the slope of a pipe, and we could set the area and hydraulic radius equal to full pipe conditions. When we do that, we would compute a flow that equals the pipe capacity. So this is a really nice way to compute the capacity of a pipe right at that moment when the water just fills right to the top of the pipe. And what I have on the screen there is the classic Herbert nomograph for pipe capacity from 1952, which, believe it or not, I still use regularly to check my math sometimes in my spreadsheets or my models. It's always good to just drop back to just good classic nomographs. On the middle of the screen, I've rearranged the Manning equation a bit and solved for slope. In this case, this would be the slope of the energy grade line or the slope of the hydraulic grade line. This is how we would compute losses, hydraulic losses or friction losses in a pipe. We can put in a flow on the right-hand side, and of course, all the details of the channel geometry with area and radius. And now models could now go and compute hydraulic grade lines and pipe performance, like I'm showing in a screenshot there from the SWIM model. Okay. And then the last example on the far right-hand side, what I've done is I've taken the equation on the left, and I've just divided both sides of the equation by the pipe area. And when we do that, the right-hand side, the A just disappears, and on the left-hand side, we get a velocity. And this is a real nice form of the equation to use when looking at actual measurements for sensors. A lot of times in pipes, when we want to measure flow, we'll use what's called an area velocity flow meter. Those types of flow meters measure two things. They measure the depth to give us the hydraulic radius, and they measure the velocity using some type of a Doppler sensor. And then we have those two measurements, and so by putting the depth in the right-hand side of the equation into the hydraulic radius, we can now generate a nice curve of what the velocity should be doing at all different depths. But we do that, by the way, by setting the slope equal to the slope of the pipe. And then we can actually see, how does our flow metering data work? Is it making sense to the Manning's equation? And is the meter working correctly? And actually, to illustrate that, I'm actually going to drop out of the PowerPoint. I'm going to show some real world data for how that would work. So give me just a second here. I'm going to switch my screen sharing. Just dropped into H2O Metrics to show some actual data. What you see on the screen here in green is a velocity measurement from a sensor I was describing in a pipe, and the blue is a depth. Let me just zoom over to a section of the data here. We have a rain event. You see rain coming down from the top in orange there. The flow spikes up, the velocity spikes up, and the depth increases. If I keep zooming in, you'll actually, there we go. You can actually see the paired measurements. At each point in time, the sensor is making a measurement of the depth and the velocity. And notice they trend up and down together, hopefully following the dynamics of the Manning's equation. But we can actually see if that's true by making a scatter plot of this data. So let me just zip over to the scatter plot tool. And now what we see on the graph here is on the x-axis, we've got that velocity plotted. And on the y-axis, the depth is plotted. And this scatter plot, each of these points is one of those measurements that I was showing before. So it's kind of a whole blob of measurement points. The black line going across the screen is kind of the top of the pipe. So I put in some parameters for this pipe, the diameter, its Manning's end, and its slope. And those parameters then can give us this Manning's curve that I described before with that equation. The reason the Manning's curve kind of has this little squiggle and it curves back in on itself, that's a function of the channel geometry. It's a round pipe. So as that pipe starts to fill up, the water starts to feel the top of the pipe and the geometry closes in on itself. And Manning's actually curves back in on itself there, which interestingly enough, for the mathematicians in the audience, that means that the Manning equation is not a function. That can make it pretty tricky to solve for sometimes numerically. Just a little point there. In this case, you can see the Manning's equation doesn't quite go through my data, but I can actually kind of adjust my Manning's end here, kind of dial Manning's end up, going the wrong way. So let me just move Manning's end out to magically at an n of about 0.13, which is a real classic value for concrete pipes. I get the Manning's going nicely through my data, and this kind of validates as an engineer that my metering data is making a lot of sense. This pipe is behaving under nice uniform flow conditions as described by the Manning's equation, at least for this time period I've got plotted here this month. If I go to the next month, you can actually see there's a period of time where we get a big rain event and the depth shoots up and actually fills the pipe up, and the pipe is now flowing in this surcharged full condition. Open channel Manning's no longer applies. We'd have to now go use full Manning's, full pipe Manning's, and get into hydraulic modeling to represent what's happening here. So that's just a quick overview of how Manning's might work in a scatter plot with some real world data. And with that, that's the end of the materials that I had. And I will stop sharing my screen and turn it over to Chris.
Yeah, thanks, Robert. While you're switching over, yeah, I'm gonna take this and move into the open channel flow arena. So I'm going to talk specifically about Manning's N and its application in open channel flow. My background, as Trevor mentioned early on, is in HEC-RAS. And so a lot of these slides and a lot of what I'm going to talk about is kind of HEC-RAS centric, but most of these principles will be applicable to just about any kind of open channel flow modeling or analysis. So when we're talking about Manning's N in open channel flow, what are we talking about? Well, it's really just a way for us to simulate resistance to movement. In the case of a river, it's the resistance of the movement of water. Here in the figure, you see presumably this mother and her daughter sliding down a snowy slope in a sled. And gravity is the force pushing them down the hill. But what's resisting it is the friction of the snow and the material underneath the sled or the tubes. Together, they form a drag force that resists the force of movement from gravity. At some point going down the slope, those two forces will balance and the velocity then will remain constant. Once the friction force overcomes the force due to gravity, then they'll start to slow down. They'll decelerate. The same thing happens in rivers. The friction force is represented by the N value, and that includes things like the friction of the bed surface itself. In practice, though, Manning's N is commonly called an ignorance coefficient. And the reason we call that, we call it the ignorance coefficient, is because that's where everything we just can't describe mathematically gets thrown, just like a junk drawer in your house. Let's say we're thinking about turbulence in our river. Well, we don't really know how to clearly account for that mathematically. Let's throw it in the Manning's N value junk drawer. What about viscosity? Again, it's a little bit difficult to describe mathematically. Maybe our model doesn't account for that. Let's throw it in the junk drawer. So that's a lot of what we do with N value. It's kind of the catch-all parameter to account for all things that may have an impact on water moving downstream or may cause resistance to that. But to really understand how you're going to use your Manning's N and how you're going to select your N value properly, you've got to know about the equations being used. In whatever model you're using, whatever software, or if you're doing computations by hand, it's important to know how the N value is factored into it. Right here, I've got the conservation of energy, commonly used in steady flow 1D modeling. Inside the conservation of energy, you see that there is a term to describe the head loss over here on the right-hand side. Okay, that head loss is made up of both friction loss, which you see over here, but also form loss. Okay, N value is accounted for, or the N value is wrapped into the friction loss term. And you can see it's just simply the length between two computation nodes. In this case, it would be cross sections times the friction slope or the energy slope. And Robert mentioned that in his presentation earlier, but this is just the difference or the energy loss from one section to the next. Now, conveniently, in Manning's equation, if we know the conveyance of the section and we know the discharge coming in, we can actually solve for friction slope because that's the difference between discharge and conveyance, is your friction slope. Okay, English units, be careful. We've got this little conversion term, 1.486, that's used. SI units, we don't need that term. Okay, so again, the friction slope or the energy loss is simply the difference between discharge and conveyance squared. Not the difference, but the ratio. Okay, the same thing is used when we go into unsteady flow modeling. The equation's different. Here we're doing a momentum balance versus an energy balance, but you can see that friction slope is still there. And it's a balance, the friction slope, it's a balance between the resistive forces and the forces pushing the water downhill. Now this is the exact same equation I had on the previous slide, it just looks a little bit different. But if you did the math or check the numbers, you would see that the N squared over 2.208 R to the 4/3 A squared is just the inverse of conveyance squared. Moving into 2D modeling. Okay, it's Manning's End again shows up as a balance to the forces pushing water downhill. But notice here in this is the full momentum equation used in HEC-RAS. Notice that we have these extra terms on the side that weren't in the unsteady flow equations for 1D modeling. This first term right here is actually our losses due to eddy turbulence. And over here we have a Coriolis loss. Now the reason I wanted to point this out is because this has an impact on how we select our N value. Because in the previous two examples, unsteady 1D and steady 1D, we weren't accounting for eddy viscosity losses or Coriolis. And if you wanted to account for that, that would have to be wrapped into your N value. So when you're doing 1D modeling, in theory, your N value is going to be a little bit higher because it accounts for these other losses that are inherent in the equation when we're doing 2D modeling. So just keep that in mind. When you do get into 2D modeling, you do have separate terms for eddy losses or turbulent losses and Coriolis, and so you don't need to wrap that into your N value. So does anybody know Manning's N little secret? What's the secret of Manning's N? Well, the secret is it changes with stage. Okay, I think probably a lot of you already know that, so it's not much of a secret, but it is very important to know because as we change stage, as we change discharge in our river, the water goes up or goes down. The N value actually is different. Now, when you get to a certain depth, it will level off and approach an asymptotic value. But as you get lower and lower in stage, that N value can actually skyrocket. It can get really large. So it's important to know. Now, when you're doing steady flow modeling and you have one discharge you're looking at, it's not that big of a deal. But when you're modeling events or maybe doing long-term simulations, then sometimes you're going to have to account for the fact that N values do change throughout. And a lot of software will give you the ability to change your N value, not only vertically, but with different discharges as well. So how do we go about selecting N values when we're building a hydraulic model? A lot of it boils down to judgment and experience. The more you've been doing this, the longer time you've spent doing hydraulic modeling, the better and better you're going to get at judgment and experience. But when you're first starting out, you're going to have to rely on other things like books and references. One of the questions on the front end of this webinar was, what book or reference do you like to use to select your N values? I still look at books and references, although I rely more and more on judgment and experience now than I used to. Equations, there's several equations out there. Robert mentioned a few of them already. There's some I'm going to show you in a second here that I commonly will use to assist in both books and references and judgment and experience. And then finally, calibration. Calibration is a very important part of hydraulic modeling, especially when talking about N values. These first three ways of determining your N value, they're going to get you in the ballpark. They're going to get you close. But calibration is going to allow you to fine tune your N value. That's where you're going to get an N value that's about as good as you can expect. Just keep in mind, if you have not calibrated your model, it's not a model yet, it's just a simulation. So by using judgment, experience, references, or equations, we're going to get close, but we're not going to have a model with that. We need to calibrate to get our simulation into a model. All right, so I want to do a little bit of research here while I have everybody attending the webinar here. If you're looking at this stream right here, based on your own judgment and experience, think of the N value that you would apply here. Now, there's no right or wrong answer, but I'm curious to see what people will use. So without looking at anybody else's answers, think of the N value that you would use, and please go ahead and type that into the chat box. And we'll take a look at what the answers are at the end of the webinar. All right, so let me show you a few books and references that I commonly go to when I'm thinking about N values in open channel flow modeling. So the first one here is, this is my my Chow book, Open Channel Hydraulics. This is a great reference, not just for N values, but anything about open channel flow. But there is a section inside of the book that talks about N values and even has a few pictures. They're old pictures, they're black and white. And most of these are constructed channels, not natural channels, but there's a few examples of natural channels in there. Not a whole lot. There's a good table in there, so you can see how N values change with different types of land classification as well. So it even gets outside of the channel and into the floodplain a little bit. This is one of my favorite books, so is Roughness Characteristics of Natural Channels. This is by Barnes, USGS researcher. And the reason I like this book is it's got great photographs in there, and it tells you what the N value is for each of these photographs. And it's got a wide range of N values, all the way up to about 0.1 or maybe a little bit higher. But my absolute favorite book is this one by New Zealand's National Institute of Water and Atmospheric Research, titled Roughness Characteristics of New Zealand Rivers. If you don't have this book and you're doing hydraulic modeling, I highly recommend it. The reason I like it so much is that they actually measure N values at different stages. And you can see here in this example how as the discharge goes up, notice what happens to your N value. It decreases. So discharge goes down, the N value increases. Okay, that's exactly what I was talking about before. It changes with stage. And so you can look at a picture in this book and you can decide, hey, am I going to be interested more at flood stage or at low flow conditions? What are my objectives of this model? And you can use that to help shape which N value or which side of this curve you want to pick your N values at. If you're looking at flood stage, then you're probably going to go with something on this end a little bit. And you might even see, in fact, in some of these examples, you see these curves level off asymptotically to the high flow N value. Couple equations. There's several of them out there. Robert mentioned a few already, but these are a couple that I use quite a bit. And a lot of this just happens to be because of where I live and the modeling work I typically do, which is up in higher gradient streams, mountain streams. Typically, you're going to find coarse bed material there as well. And I found both of these equations to be very good at getting me a good getting me close to an N value that I'd like to use. What's really interesting about Jarrett's equation is you can find that as your bed material gets larger and larger, the slope gets really large. You get into these higher gradient mountain streams, the N value can actually skyrocket. It's really, really high, especially for lower R values, hydraulic radius or radii. So it's a little bit revealing to see what N values you can get. I've gotten N values up in the range of 0.12, 0.14 for mountain streams. And so it's always a good check to make sure you're not underestimating your N value. I give these at best plus or minus 20% though, accuracy. So even if you know, I get agreement between these equations, or I'm feeling pretty good about one or both of these, I'm not going to consider it any better than plus or minus 20%. And to get better than that, really the only way is to calibrate. Calibration is just the adjustment of a model's uncertain input parameters to reproduce a measured event, something you have historic observed data of. Without calibration, your model is just a simulation, as I mentioned before. Okay, this is where you're going to fine tune your N value and really dial it in and make your model useful and able to answer questions with. Here in this example, you can see we've got our simulated values in red. This is our computer model observed in the black dots. And you can see at the high flows, we're actually under predicting stage. And at the low flows, we're over predicting stage. So at high flows, that's telling me if, let's say, everything else is perfectly accurate, which it's not, but let's say for the sake of argument it is, and we're just focusing on N values, then that means at the higher flows, my N values are on the low side. They need to be elevated, but at low flow, my N values are a little bit high. Okay, and you can see the conundrum we have here, and that is our N values are going to be different depending on the amount of discharge or the stage of flow in our simulation. So in this case, we would want to have a modeling software package that allows us to vary the N value with discharge or with stage. Let's talk about some special cases with N values. These are things that classically have been thrown into an N value because we don't really know how to describe them mathematically, or maybe the software we're using doesn't fully describe them mathematically. Turbulence. Okay, you see a river like this. If you were to use an N value from one of those picture books or an equation, you may not be capturing all of the losses here, given the amount of turbulence you see here. What about debris? If you've ever seen a debris flow, or if you haven't seen a debris flow, I highly recommend you check it out on YouTube. They're fascinating to watch, but it's amazing to see this mixture of water and woody debris and mud all coming downstream, and you certainly wouldn't want to get in the way of it, although it doesn't move too fast typically. But all of that debris that's entrained, both in the water and floating on top of it, adds to the energy loss. And in a model like HEC-RAS, the only way to account for that is by increasing your N value. What if we're doing some urban modeling and we're simulating floods in a residential area, like you see right here? Each one of these buildings actually blocks the movement of flow, but as water is able to get inside the building, there's a volume component that we want to account for. And so how do you use Manning's equation to simulate water that's taking up space, but it's not moving because it's inside the building? You do that with a really, really high N value. And so that's a common technique in hydraulic modeling when simulating a building, where you want to account for the volume of water that's inside it, but you want to make sure the water's not moving. You have a very high N value. I've seen N values of, say, 10 or even 100 used to simulate this phenomenon. And here we've got a steep stream. And steep streams, you typically have low stages. In fact, the stage is so low, it's on the order of magnitude of the roughness elements themselves. If you remember what Craig was talking about earlier, that this gets us into what's called a sheet flow condition. Okay, now this is not classically what we might think of as sheet flow, but in theory, that's what's happening here. You've got water that's so low in depth relative to the roughness elements that the N value just skyrockets. And Jarrett's equation actually will pick this up. So that's why I like to use Jarrett's equation when I'm modeling a stream like you see right here. And then what about 2D modeling? I mentioned this earlier before, but 2D models typically will include turbulence in their equations. And so we don't need to throw that into the Manning's N junk drawer when we're doing 2D modeling. It's actually computed. So in that case, our N value may not be quite as high. And getting back to sheet flow, this is an example of sheet flow that I found just walking down the beach. Let me see if I can get this video to play here. And as you watch the water recede down, you'll see it all of a sudden slow down drastically right about now. And that's where the water depth gets to be about the same as the height of the roughness elements themselves. In this case, it's the sand particles. You can see some bed forms form during that transition as well. Okay, so that's where we're going from regular flow to sheet flow. Another example of sheet flow, water moving through grass. Here we see water is actually shallower than the height of the grass blades themselves. Okay, as water's moving through these grass blades in this condition, the N value is going to be extremely high. And then again, this mountain stream gives you another example of sheet flow. And then I wouldn't be genuine if I didn't include a slide here on model stability, because this is oftentimes a reason why we may change our N values. Now, I want you to be cautious about this, because while higher N values gives us higher depths, and higher depths mean more numerical stability, we shouldn't increase our N values just to achieve numerical stability. There has to be some logical reason behind it. Now, if we can come up with an excuse for increasing our N values, maybe there's a lot of turbulence, or you're in a steep mountain stream where you have large bed material, you can justify increasing your N value. And by doing that, you're also going to increase your model stability. So it's important to understand that. So in dealing with N values, I want you guys to take this back with you. And one is always do a sensitivity. You need to acknowledge the fact that we're not going to be exact. We don't know what the N value is. We don't know what all the roughness losses are. And so by doing a sensitivity, we can get a good idea of the range of potential results that we might have in our hydraulic model. And that will allow us to make decisions on both design, but also on anything else that you're using your model for. Okay, calibration is very important as well. This takes it to the next level, and this allows you to fine-tune your N value based on real historic data. And then again, when talking about doing design work, you're typically going to lean to the conservative side of things. So after you do a sensitivity analysis, you can figure out what that is and how a conservative N value might affect your results. And then finally, I always like to throw in a plug for probabilistic modeling. It's an interest of mine, but this is exactly the reason why we need to do this, is because of the uncertainty with N values and other coefficients that go into our hydraulic models. Keep in mind, your model is wrong. Let's try to make it useful by using these techniques here I've mentioned. All right, so what did you guys select for your Manning's N? I threw out a number of 0.065. I'm going to turn it back over to Trevor, and we can see what the rest of you put in for your N values.
Great presentation, Chris, Robert, Craig. That was very interesting. But I looked at those N values pretty seriously, and it goes all over the place.
I just popped them into a spreadsheet, actually.
Oh, well done.
Because I'm nerdy that way to run the statistics, and it averaged out to 0.06 based on the responses.
All right. Yay, that's good.
What an amazing outcome. Yeah, thanks, Craig. That was a really good thing to be doing. Average it out. Because thank you, everybody. There was 100 answers there all of a sudden. I'm trying to do an average in my head. No, not possible. Good, Craig. Thank you. So it came pretty close to what you had thrown out there, Chris.
Great. Yeah, that's good to hear.
Somebody asked the question, what would you do in a modeling software package that doesn't allow you to do depth varying roughness? And I'll just mention one quick hack that I use sometimes is to run it once as it is, and then export my layers, my water surface elevation in terms of depth. I'll export a 1 meter or a 2 meter or a ½ meter depth layer. And then I use those polygons as my geospatially varying or spatially varying roughness layer. So that's one thing you can do. I will throw two questions out there. Maybe I'll throw them both out at the same time. First to Robert and then to Chris. Robert, one of the questions that came up is if you are looking at pipe flow, and I think you've answered this on there. You know, why would you use Manning's equation if it was developed for open channel flow in natural conduits? Why would you commonly use it for pipes? And you may want to talk about the other alternatives once you get into pressure flows and how Manning's more appropriate for open channel or pipes that are not quite full. And then Chris, one question that comes up after this that we can lead into straight into is the amount of or the differences between 1D and 2D models, and if there are any guidelines. You mentioned that some things might get double counted when you run a 1D versus a 2D model. You know, some of the things that a 2D model is accounting for might not be entrained in the roughness value you pick, but are there any sources and any guidance? So I'll just leave those two questions from the chat line, and then we can answer some live. There are many, like somebody mentioned, there are many software packages that do depth varying. I see that comment coming up. There are many software packages that do, but if you're stuck with one that doesn't, in the meantime, there are some hacks around it. So with that, I'll back off and give that time over to Robert to start answering these questions.
I'll go first, and Chris can follow up with a second question. It's a great question. If Manning's was developed for open channel flow in natural conduits, why is it commonly used for modeling of pipes? And my answer on that is I think of a pipe as just a conduit like any other that just happens to have a lid on it, a top. And the Manning's equation is certainly capable of describing the channel geometry right up to where the pipe curves back in on itself and becomes a closed conduit. It also works really well for pipes. And then Manning's N is a fairly simple way to represent friction. There's lots of published values for Manning's N. I think all these things are reasons why it's taken off and really become widespread for use of not only natural channels, but also pipes. Craig referenced, is it only appropriate for pipes under open channel conditions? Well, it's used there a lot. It certainly works just fine under pressurized conditions as well. You still get a radius and an area in a full pipe. And the Manning's equation will give you either a flow or a slope of the energy grade line, depending on your application, in full pipe as well. And so that's why I think in the swim model, you see Manning's as the default for even modeling full pipes inside of swim models. I think in other modeling applications, like in water distribution system modeling, you'll often see the Hazen-Williams equation, which I talked about earlier, and the Hazen-Williams C. And I think the reason why the Hazen-Williams equation is, and I actually searched around on the web and I talked to some other engineers about why do we use Manning's for pipes and conduits and we use Hazen-Williams in water distribution modeling. And I don't think anyone had a good answer. And the best thing I can come up with is just, I think Hazen and Williams, when they developed their equation, did it for full pipes in a water system. And that's just a tradition and history. Whereas Manning's developed it for channels and it works well for pipes. And so tradition and history has us use Manning's there.
Yeah, Robert, I'm really curious to know about pressurized pipes too. I mean, my intuition is that the N value would go up considerably once the pipe pressurizes. Have you seen anything like that in your measurements that you've done or your experience, or do you usually keep it the same N value in pipes regardless of open channel or pressurized conditions?
Yeah, great question, Chris. I have seen modelers use a varying Manning's N for pipes as the depth changes, just like you do for natural conduits. But once we hit that full pipe, we usually use textbook values and we don't see some sudden spike or change in the Manning's N when the pipe is full. And I think that's because we get consistent velocities. We get similar velocities whether we're an open channel or full pipe. We're not getting a drastically different velocity profile just because the pipe is full.
Thank you for that.
I think most of the questions have been answered online. Go to the answered questions or the
Yep.
dismissed questions to see some of those there. Again, if Chris, if you want to just comment briefly on any standard methods for flows from 1D versus 2D, and then we'll make a plug. Everything we do in 1D and 2D is depth averaged. If you want to get into that varying depth profile with the velocities, come along to next week's webinar on 3D. That's a plug there. But I'll let maybe Chris take a minute or so to just answer that question. Are there any standard ways to go from 1D to 2D to avoid double counting things in your N value? And then maybe we just go back to Trevor and wrap it up.
Oh, the 3 books recommended by Chris, but just the last comment there. Sorry, you'll see on the question and answer line. Maybe somebody could get that while Chris is answering.
Sure. Yeah. Well, I was just going to show I saw this question in further up the list, but this book that I showed you right here, this is Harry H. Barnes, USGS. I don't know if everybody can see that.
Roughness characteristics of natural channels.
Roughness characteristics of natural channels. You don't have to buy this book. You can find it online. Just do some Googling. I think a lot of people have access to Chow, which was one of the other books. And then Hicks and Mason, which is the one from New Zealand. This one right here, you might have to buy. I don't know if that's available online. Now, to get to Craig's question or the attendee's question about 1D and 2D N values, to be quite honest, I don't put a lot of thought into it. I still use the same approach I use for 1D modeling as I do for 2D. I do recognize that the N value can be a little bit different, especially if you are using the full momentum equation, where you're introducing losses due to eddy viscosity and maybe the Coriolis effect. But that just underscores the importance of calibration. Okay, that's where you're going to fine tune it. Okay, if you can get within 20% on your first guess, whether it's 1D or 2D, you're doing way better than I do. So yeah, for that reason, I don't put a lot of thought into the differences between 1D and 2D, but it's important to know, and it actually gives you a little bit of background and ammunition when you're trying to defend your use of N values, say to somebody reviewing your model work.
Fantastic. I reckon we'll leave it there. Any final comments, Robert or Cray? All good?
I think we're out of time. So
Been
thanks.
Absolutely fantastic. Thank you very much from all over the place. Seattle, Michigan, Perth. Absolutely brilliant. Thanks everyone for participating. There's a feedback form coming up straight after this. There's a recording we'll email to you. Look at the free webinars coming up the next couple of weeks. Oh, yeah, they're coming fast. We're doing this every month. And the online course, I really strongly recommend, Modeling Structures in HEC-RAS. I think it's the same. Are you in that, Cray and Chris?
Yeah, I'll be teaching that one next week. I get Chris's input on these things.
Brilliant.
And Chris has got his own courses up and running too on the blog. Go to the HEC-RAS blog and you can see some of Chris's courses too. And then go to Robert's, make a plug for Robert's software as well. It's go to his website. There's some very handy tools there.
Great. So if you want to hear these gentlemen, you go.
Sorry, if I can make a really quick announcement too. We just had the second HEC-RAS Pub and Grub, and the for those of you interested in HEC-RAS modeling, there are some fantastic presentations that are available to preview some of the really cool things coming. So go to the RAS solution, check that out, and you'll see all the good stuff coming.
One thing you can't do online, Pub and Grub. That's really impossible. And Robert's blog there at H2O Metrics. Is that right, Robert?
Yeah, that's right.
It's up on the chat line. You'll see the connections up on the chat line. We won't take any more time over this. It's been absolutely brilliant hour. Thanks everybody for being so involved in the discussion. We'll call it 1 hour for there and say bye for now. Thanks, Cray. Thanks, Chris. Thanks, Rob. Thanks everyone for joining. We'll see you next time. Bye.
All right. Thank you.
Thanks.
Bye, everybody.
Subscribe to this YouTube channel by clicking the subscription button. For future webinars and online short courses, please visit our website at australianwaterschool.com.au.